The effect of ambient conditions on volume hologram parameters. A recording medium to produce volume holograms should, as already mentioned, be about 1 millimeter thick and ensure the invariability of hologram structure in the course of treatment and operation. The temperature is one of the main ambient parameters with its effect to be allowed for when handling HO. Temperature variation causes changes in both linear dimensions and refractive index of a sample. Table 5 lists characteristics that enable assessment the temperature-induced changes in parameters of samples of recording materials in use. Note that the changes occurring in samples at varying ambient temperature are, as a rule, interrelated. i.e., a drop in refractive index is due to an increase in sample dimensions, its expansion, while sample contraction causes the index to grow. At the same time, the processes of hologram recording and post-exposure treatment have a selective effect on sample parameters. Either recording or post-exposure treatment necessarily results in a refractive index change, with the geometrical dimensions of the medium remaining practically the same. The media are then called shrinkproof, or undergoing slight changes, media with negligible shrinkage. Media on silicate glass base are commonly believed to be shrinkproof, yet when the holograms are recorded on PTR glass samples, see Table 1, the average refractive index changes in the course of thermal post-exposure treatment by a noticeable value 10^4, Gleboff, et al., 2002. This is to be allowed for in design of with prescribed performance. The temperature effect on the changes in refractive index and dimensions of samples used to produce volume recording media. As seen from the data of Table 5, the changes in parameters of polymeric media at varying temperature are substantively, several-fold, larger than those of media on the base of silicate glass and crystals. In addition, polymers exhibit a property to take up moisture, which in turn causes changes in sample thickness and average refractive index. Therefore, handling the polymeric samples makes it necessary to maintain the ambience stable. Experiments on recording and reconstruction of holograms, produced on silicate glasses and crystals, are held under ambient conditions, maintained as a rule at the level of standard conditions of a research laboratory. Temperature variation is plus or minus 1, humidity variation is 3 divided by 5%. The accuracy, within which one should maintain the ambient temperature and humidity for the conditions to be considered stable for polymeric samples, is dependent on the recording medium properties and the prescribed requirements to hologram parameters. The present section gives the results of experiments on the temperature and humidity effect on parameters of hologram gratings, 1.0 divided by 1.4, thick, which were produced on samples of polymeric material definite recording by radiation with lambda equals 488 nanometers at spatial frequency nu equals 300 divided by 500, 1. The results obtained for a PMMA-based polymeric recording medium can be used to optimize the conditions of experimental operation of different polymeric samples in recording and reconstruction of information. The effect of temperature on parameters of polymeric volume hologram gratings was assessed by observation of behavior of low-frequency interference pattern, IP. The schematic diagram of the experiment is given in Figure 6. It was carried out with the use of a stand intended for hologram recording, the same where the hologram under study was recorded. Hologram grating was mounted into the scheme in the position it had during recording and illuminated by two coherent beams I1 and I2. Each of the incident beams was diffracted by the hologram structure with formation of its own diffracted beam. Beam I1 formed diffracted beam I1D that propagated in the same direction as beam I20, and beam I2 formed diffracted beam I2D that propagated in the same direction as beam I10. When the hologram was shifted, an angle, 2 phi, was formed between beams that propagated behind the hologram in the same direction, I1D and I20. I2D and I10, and the IP was formed is the space where the beams superimposed. At a turn of the hologram through angle phi equals 0.1 rad, the pattern period, d, has according to Bragg condition the value d 2.5 mm. Diagram of the experiment on creation of low-frequency interference pattern. I1 and I2 are coherent beams of collimated radiation with lambda equals 488 nanometers, 2 theta is the angle between beams I1 and I2 in the air, Ho is the hologram grating, 1 and 2 are temperature sensors, I1D, I2D, I10, I20 are beams of radiation diffracted by a hologram grating, first in 0 orders, 2 phi is the angle between beams that form the low frequency IP. The forming interference pattern can be observed in each of propagating beams, I1 and I2, with a screen installed perpendicularly to the beam propagation. The IP was recorded using a CMOS matrix of a size that allowed recording the observed interference field in full and obtaining interferograms imaged in Fig.7b. The interferograms were shot at actual size simultaneously with temperature control. The temperature sensors, mounted onto the sample on the side 1, and on the side 2, in close proximity to the observation area, allowed carrying out the control with accuracy 0.1. Before the experiment started, the hologram was set in the position, where the IP had the maximum period that provided the possibility under those conditions to process interferograms and perform quantitative measurements. To measure the temperature, a warm air jet was directed towards the hologram on the side 2 and the sample was heated up to temperature equals 32 degrees. The interferograms were shot in a stationary state of the scheme, with the sample cooling down after the action of warm air. The difference in readings 1 and 2 was within the measurement's accuracy. Changes of the period of the low-frequency interference pattern, IP, at variation of the temperature of polymeric hologram grating with nu equals 350 mm -1, recorded on a sample of DFIN material 1.2 thick, B, IP images at hologram temperature 21 degrees, and 27 degrees, B, D, processing of interferograms given in A and B, respectively. E, dependence of IP period, D, on sample temperature, dashed line illustrate the character of process. The experiment was carried out under the following conditions: interfering beam diameter, D, 8 to 10 mm, angle between beams I1 and I2, 2 theta, 10 degrees, lambda equals 488 nanometers, angular selectivity of the hologram under study, delta theta, 1.7 rad, temperature variation interval 21 to 28 degrees. The obtained interferograms and the results of their processing are given in Figure 7d. The dependence of IP period change on sample temperature is given in Figure 7. As seen, with the temperature growing from 21 to 28 degrees, the IP period changed from 1.8 mm to 0.7 mm, which corresponds to a change in angle 2 phi, theta max shift, by 0.43 rad. The experiment showed no change, within the measurement's accuracy, in the IP period, measured before the start of measurements and after the sample cooled down to the room temperature. Thus, one can estimate the effect of temperature variation on parameters of polymeric hologram 1.2 thick with spatial frequency nu equals 350 mm -1 as follows, with the temperature changing by 1, the change in the diffraction angle, theta max shift, amounts to delta theta max equals 0.06 rad, i.e., the hologram under study has thermal shift 0.06 rad /. Note that the temperature effect on parameters of polymeric reflection holograms, recorded on samples of rioxin material, Sukhanov et al., 1984, demonstrates the magnitude of changes on the same order. With the temperature of rioxin sample changing from 24 degrees to 29 degrees, the shift of lambda max in the spectrum of reflected radiation is from 532.1 nanometers to 532.6 nanometers, spectral interval of reconstructing radiation, delta lambda less than 0.01 nanometers. Thus, the studied hologram, thickness 1 mm, nu greater than 3000 mm -1, spectral selectivity, delta lambda equals 0.15 nanometers, intended for the use as a narrowband spectral selector, had thermal shift delta lambda max equals 0.1 nanometers/K. It has been established that a DFIN material sample, a disc 40 mm in diameter and 4 mm thick, when immersed in water in the temperature range, 20 divided by 30 degree, takes up to 1.5% of water with respect to the sample weight in air-dry condition at relative humidity of the ambient air 50%. Taking up moisture changes the average refractive index and thickness of the sample and, accordingly, characteristics of recorded holograms. The effect of varying humidity of the ambient air on the polymeric hologram parameters was studied at an experimental stand of a design that provided for an enclosed volume around the hologram to maintain humidity 90%, much higher than normal conditions, and for conduct of long-time measurements, several hours. Figure 8 shows the optical diagram of the stand. Figure 8, and schematic drawing to illustrate possible changes in polymeric sample dimensions under moisture takeup, figure 8b. The stand was used to measure the angular selectivity contour of a hologram at a one-time fixation of all contour data. The hologram was illuminated with a divergent radiation beam, the intensity distribution of the diffracted radiation, angular selectivity contour, was recorded by a CMOS matrix of a camera. The results of processing the experimental data are given in figure